Alright, hell yeah. So we got material mechanics. This was a problem sent to me. So pretty sweet. If you got questions, you know what I mean, send them my way. Especially if you're stumped on like one aspect of something. Now on this one, I can't reinvent the wheel. I really want to because it involves shear failure, you know what I mean? Or just shear stress and how much, what shear strength. So let's talk about that. I think it's easiest to talk about something in compression, a force in compression. I use a steel, like 1-inch steel bar. I think that's kind of the easiest. Get to work in U.S. customary units. And with metal or with steel, you can compress it the same load. So we get a load there. You can compress it the same amount that you can stretch it. And then since we're talking about material mechanics, I think the first kind of fundamental of material mechanics is that you can put a load on something and, you know what I mean? Well, I guess it's a relationship. If you put a load on something like stretch it out, it is going to stretch. It's going to change in length. And then kind of the second fundamental maybe is that if you keep your loads within some sort of limit, which is pretty much the usable strength of the material you're working with, you know what I mean? There's not like a halfway point where you like, uh-oh, we passed the halfway point, now we're stretching it out permanently. No, it's like the second something actually stretches, turns into plastic, deforms, bends, it's kind of when you went over like the actual capacity for that material. And that capacity is a high enough number that most every structure that gets built is a lower number than that number. And if you are a lower number than this max load that you can put on it, what happens is that every molecule returns to its original length, shape, volume. You know what I mean? So if I put a load on it, it stretches. But if I let go of that load and get the material back to its, you know what I mean? You can just, so yeah, you could build a skyscraper. You know, I mean, putting, I-beam columns on top of, you know what I mean? Wide flange columns on top of wide flange columns. They're all going to compress, and so you are going to get a change in length out of all of these. But then you can unbolt the entire skyscraper, and guess what? Those steel bars, or those steel like wide flange beams, I-beams, whatever you call them, are going to be the exact same length that you bought them. And so that's kind of a fascinating aspect of material mechanics, where as long as you're within that limit, you know what I mean, you can, this material has a hell of enough strength. And then the other aspect, you can get more strength out of something. So something can permanently squash, more than that change in length that we were talking about, or something can overly stretch, where if you let go of the force, it just kind of stays that length. It doesn't go back very much at all. And yeah, and so you can stretch things out. You can get a little bit more juice out of it. But the kind of the chart on that is like, hey, things, if you put a load on something, so I think it's easiest to do like a load displacement diagram. So we're going to, put some sort of force on this 1-inch bar, and it's going to change in length. Cool, and this is the change in length that it's going to do. We reach a point where, like this is going to be your max load. Where if I put more than the max load, I can't, and this line just flatlines. But I do, once I get up to here, I do see just a change in length. You know, I mean, the thing is just turning into taffy and then breaking. What really happens, it actually gets stronger, and theoretically, because it necks down, like it gets hella strong. You know what I mean, and then kind of breaks. You know, kind of like that. But for our purposes, you know what I mean, I think it's very useful for most materials is just to assume that if you get to this max load, that is the breaking point. And just like right here, I consider this, you know what I mean, where lives get lost or people lose their jobs. I mean, for most things that you're building. All right, hell yeah. Because then the other aspect of material mechanics is that you have to go test stuff and then put numbers to things. And that's where I really do think like shear stress is very empirical. Because then, later in the chapter, what they talk about is, and I've done this before, especially with my little diagram, we've lost a lot of air out of this thing. But in shear, okay, cool, you're going to maybe put an upward force and then a downward force. This is kind of, this would be negative shear, but anyway, they do it like this in the diagram. And if you do that, if I put an upward force on this whole thing's just going to move up. That's kind of like mechanics, Newton's laws of motion. Put a force, it's going to go that way. Now I'm going to put a downward force. But what's going to happen is it's just going to turn. Okay, so I'm applying an upward and downward force. Nothing, it's not doing this. And in the diagram, you will get a shape like this. And the only way that you're going to get that shape by applying an upward and downward force is if I come in here and apply a force this direction, and then come in here and apply a force that direction. So I'm going this way, and then up, and then I'm going down, and then this way. So it's pretty cool I can do this just one person. You would want to do this in a team of two. This would be a great demo to do kind of at a college. Get a balloon, draw a square on it, and just get two people. If I pull up and down, the other person would have to pull this way and this way. So I hope that's obvious. And what happens is that you get this shape to form. So this, and then so let's put this. You have to have this force and this force, and they're equal. So those are your shear forces. These two make a moment going that way, kind of a torque that in dynamics would cause a rotation. These two forces counter that, and those two torques, those moments balance. And then how to draw the actual shape that this deforms is I would start with your four corners. Just know that this side is going to go up, so we're going to go up. This side is going to go that way, so we're going to go that way. This is the only point that we're going to keep the same location. When this went up, this one went this way, so we have to draw a point right there. So anyway, so this one goes up, this one goes over, but because we drew this one and then this one, but then we have to, make it right there. I don't know if that's how I do it though, you know what I mean? Move this one up, move this side over, and then just realize that, yeah, this side is right there, this side is right there, but this is your, yeah. And then anyway, so what happens with this is that these lengths stay the same. So we have no change in length of this. But what happens is that you get a compression from here to here. Like this compresses. And then you get a lengthening from here to here. This lengthens. And one of the aspects that, I just kind of pointed out in material mechanics, that if something changes in length, you know what I mean? It gets to a point where it can only change in length so much, and then it breaks. So, and I'm just mentally and visually, it's very good to call this is the proportional limit. This is kind of the yield. I kind of forget what's the difference between the yield and the proportional limit. It's like one, damn it, I don't know the difference. They're extremely close to each other. Maybe they're the same points. I forget on that diagram. But basically, there's a point where you can take it to that max load, back it off, everything goes back to the same molecular shape. But if you go any farther than that, then you start to get into bending. All right, hell yeah. And then this is where like I need to like go to a college level, high end, university and study material mechanics, because they use a lot of simple models like this in the book. Like I would say the fact that so for our problem we have a glued joint right here, and then they're just saying that you have a shear stress, which is a pressure, just say a PSI. And I guess it doesn't have to be synonymous with pressure, you know what I mean? Because if you have like a you know, a little cube and you drop it into the ocean, hey, you get pressure like on all sides. You know what I mean? And then when axially, you know what I mean, we have this same cube, but we're only getting force down and a force up. You know what I mean? So we don't have the pressures out to the side. And then so, and this is kind of a side note, but this is where you could throw any structure at the bottom near the Titanic, and as long as it's not filled with air, as long as the pressure can be everywhere, all the molecules will change. You will get strain. You will get a change in volume, but in all directions. And like right here, we're going to have a change in length this way. Now, we're not necessarily going to have too much of a change in length this way. We do get that due to Poisson's ratio. And but this scenario, you can only change its length by so much before it breaks. Or if you drop this in the ocean, if you can turn this into a neutron star and it's not going to break. You know what I mean? So that's kind of fascinating that you can have hella pressure on something, and as long as it's in all directions, it's not going to break. All right, hell yeah. So I guess the other aspect of material mechanics, let's say our bar is just like 1 meter. Turn that into millimeters, just because how much can we actually change this in length? How much could we compress or lengthen this bar? We can only lengthen it 2 millimeters. I mean, that's hardly visible. So we can have a whole meter long bar, but we can only lengthen it 2 millimeters. Now, that 2 millimeters adds up if you're talking about the Golden Gate Bridge, you know what I mean? And if it lengthened every 1 meter, if every 1 meter of the Golden Gate Bridge lengthened by 2 meters, you just run the math, you know what I mean? So now we're just like about 1,000th. So whatever 1,000th of the Golden Gate Bridge is, that would be a 1 millimeter per 1 meter. You know what I mean? That would be a substantial distance. Now when it comes to heat change, you're not going to get, like, let's say you could have 2 millimeters. Maybe spec is saying that you can only lengthen it 1 millimeter, or just half. And then temperature fluctuations would be another order of magnitude lower. You know what I mean? It's going to be for every 10 meters, for every 10,000 millimeters or 10 meters. I don't know the number, but it's going to be at least 0.1 millimeter in change in length or 0.01. So it's either 10x lower or 100x lower due to temperature changes. Okay, so now there is, so when we shear something, we talked about how we changed its length this way and compressed it this way. And these two leverage each other where you get twice as much all right, let me talk my way through this, because from things changing shape, if I have this shape, kind of a longer bar, and I do stretch it out to here, what's going to happen, then let's say I stretch it 1 inch. What's going to happen is it's going to, yeah, so let's say this is just like a chunk of rubber. A chunk of rubber could do this. You would have a 1 inch rubber, holy Toledo. Maybe rubber wasn't the correct choice, but it's the only one elastic, so we'll keep everything nice and square and boxy. But anyway, so hell yeah, so you can increase, so we'll have make this 3-dimensional, so you can increase the length by 1 inch, and due to Poisson's ratio, you know what I mean, as you're stretching that, the molecules kind of come down, so this height gets reduced. And the opposite is also true. If but it's not equal and opposite. So if I have this same shape and then I compress it to here, does that mean that it shoots out all the way to this shape that I had? No. It just means that so if I take that shape and compress it to here, only a third, so it's about a third. So if this height decreased to there, then this width shoots out about 1/3 of that. So, all right, hell yeah. So, and I need to rough this out way more. So I'm going to use this video to do this. Is when we do shear something, we actually, if you do the element at a 45 and go through all that, it's actually a nightmare. I mean, it's just like, you think you're good at doing, taking a beam, doing the reactions, and then cutting it in two, and then having a normal force, a shear force that causes a clockwise rotation, and then a moment that would cause it to smiley face, you know what I mean? Like, even if you're just stellar at that, I think it's a challenge to take this diagram, and they don't even show it like you in forces. They do this. They just say, hey, this isn't even a force yet. It's just a shear. It's a shear stress. So it's a pressure, and then, hey, this face has some sort of area. So if you did, and it's a 3D block, so if you did have area on this face, then to find the force is that shear pressure, which is, force per length squared, PSI, newtons per meter squared, or pounds per square inch, and then you're going to multiply by the area, length squared. So then the units cancel and you get force. Cool. And then if you go through all that calculation to do what happens at a 45, well, you get this. You get this force pulling this way, this force pulling this way, and this force pushing the equal amount in compression. And the fascinating thing is, as long as you got, like something, like if I welded a 1-inch chunk of steel to a wall, and then maybe kind of welded on a hanger here, and then put a force down on this. So here's my load. Well, hell yeah, I would have this load at the wall, P, but then, like we said, the thing's not spinning, so I would get all of those equal, forces to counter, and we would get, you know what I mean? Yeah, this is where I have to do a really good job of, like, not saying wrong things, because one of the things from free body diagrams is, like, is there a force right here? No, there is no force. Is there a force right here? No. Anywhere where there's just air around this thing, there is no external forces. But yeah, so I need to up my game and then start cutting this stuff up, because at a certain point you will get an element that looks like this, though. You know what I mean? Take an element where you do have in this case, you would have a downward force and upward force, and if you had those two, you would have to have those matching forces. And if you had that, and you actually took this element and rotated it at 45 degrees, which just makes life extremely maddening. But it's no different. Like, I don't think it's too far. I mean, it's what happens at the global level. You know what I mean? Like, if you do have two steel plates and then a chunk of rubber, and then you're pulling on these, like this chunk of rubber does bend like that, and it turns into that shape. And if we just had a square chunk and did that same thing, then our chunk would turn into at least this shape. You know what I mean? Where well, yeah, and let's just say these lengths don't change. You know what I mean? So the actual overall height would kind of squash down, but let's say these lengths don't change. But what we do see is that this point and this point get farther apart, and this point get closer together. Damn it. The whole take-home point of this is that if these 2 points get too far apart, it's going to break. So that comes back to, like, what material mechanics is like, hey, if I see a change in length of more than 2 millimeters when I pull on this 1 meter bar, like, and then kind of the bummer of material mechanics, because it's more complicated than that. Like, everything, like every aspect of material mechanics can be, like, as complicated as you want it. But I'm just saying, hey, if you set here as your max, or where I like to call, like, hey, that's where things break. It's not where things break, but it's where things, maybe you lose your job or people lose their lives. So that's the first place that bad things will happen to you, your company, or to other people. All right, and that happens maybe, for steel, when you lengthen a 1 meter rod by 2 millimeters. And so let's say I have a 1 meter by 1 meter sheet, or like just even like a block of steel, you know what I mean? Nothing's moving that except like the Hulk. And we're going to do that same thing. We're going to put those shear forces on it, and we're going to get it to look like this. Well, so this is one of the most important fundamental aspects of material mechanics, because they do state it. This is how you actually like relate shear to your normal stresses. Because the take-home point is, let's say your shear stress, your normal stress for axial, tension in a steel rod is 58,000 pounds. Well, now the question is, like, what is your shear stress for steel? Like, if I, shear it sideways, take a bolt, do that. Well, it's about half. It's going to be about half this number. And then, like, where does that come from? Well, it comes from this. Because, and I'm just going to go one step farther and say, like, hey, if any 2 points get farther than 2 millimeters away, so if this distance, if this distance was 1 meter or 1,000 millimeters, you know what I mean, and then I turned it into this shape, and this length got to be 1,002 millimeters. Well, that's when this breaks, and these bonds break, and we get a break at a 45. So this is where if you take a piece of chalk and you do, might as well make this video exciting. Alright, my brother said don't do this without drawing the square on it, you know what I mean? I've never actually drawn the square on it, but it just makes sense. And what we're going to do is we're going to do exactly like our thing. We're going to put an upward force and a downward force. Now those are the forces that I'm going to apply. But what happens when I do rotate these, like there must be a force this way and a force this way. Because if I did this, the whole thing should just spin, right? But it's not. So like if I'm holding this way, and where the hell are we going to see the break? Well, we're going to see it at a 45. Let's do it. Hell yeah. Alright, so that was probably the best part of this video. And now I think that bought me another hour of just nonsense. Alright, sweet. Alright, hell yeah. So let's talk about why that broke. The only reason that thing broke was that these molecules got too far apart. And chalk doesn't have the same dynamics as steel. You know what I mean? Where I think that's why, like, if you have a ductile material, you can like take Play-Doh. You know what I mean? You can just do this in a circle and then you just kind of start spinning and spinning. But also, yeah, so a ductile material won't break like this. And so what happens with chalk is really strong in compression, but is hella weak in tension. So that just really shows you that, hey, if we tension, and tension from material mechanics perspective is just you're changing the length. So you can say chalk can only take so much tension before it breaks, or chalk can only take so much elongation. So that's the fact. That's like the two things. That's the fundamental of material mechanics. They're both saying the exact same thing because it's all empirical anyway. I mean, we do empirical tests and we see that we do have kind of a linear relationship, that if I put this max load on it, changed that much length. If I put half of that, hey, it only changed half the length. And this goes to chemistry, is that, well, actually, I don't want to say more things that I don't know, because a lot of electrostatic forces are, related to the distance squared. But, like, yeah, so it's just fascinating, even with molecular chemistry, that I think, I'm just going to go out on a limb, but most things, if you move them just very slightly, will move linear elastically. You know what I mean? So they shifted a little bit, you put a force, you let go, they go back to the original shape. You get to a certain perspective where, like electrostatic charge, if things are like ionic bonds are electrostatically charged together, you get to a certain distance, though, that electrostatic charge it's like gravity. It's like you get far enough away from Earth, it's like, hey, you don't have to get you get twice as far from the center of the Earth, and your weight goes down by 4. You know what I mean? It's the distance squared. Okay, hell yeah. All right, so yeah, this is kind of just showing that if things get far enough apart, then they break. And then what happens here with this little shearing thing is at a 45 we get two things going on. One, this load might change its length to that breaking point, but then this load sideways compresses it, and when you compress it, you do change its overall length. And so I guess I'm going to use this problem to kind of go over. This is kind of the like I have not even started on this problem. I guess this is just the video that I wanted to make, and I think it's good. And so let's take this 45-degree shape. I think we're done with this problem. All right, hell yeah. And so and we're just going to make this 1 meter by a meter. I think it is best to do that. So we have 1,000 millimeters by 1,000 millimeters, and we're going to compress it in, and then we're going to tension it out. So with the same load. And so let's say this is just a 1-inch cube block, and let's say we put that 58,000. I always like to use numbers that I'm familiar with, but we got 58,000 pounds. We have if this is a 3-dimensional block, we got a surface area of 1 inch squared. And when we put this 58,000, that's the max that steel can do. So it's going to change in length this direction. This length now is going to be 998 millimeters. And when we do that, Poisson's ratio says, hey, we took something that looked like this, squished it, so now it is narrower, but it gets longer. And it doesn't get longer in equal proportions. You know what I mean? We squished it by 2 millimeters. Does it change in like this way by 2 millimeters? No. But it's about a third. You know what I mean? And for steel, it's 0.3. It's 30%. So so this length now increased to plus 2 millimeters times 0.3. So we got, what would that be? 0.6 millimeters. So now this length now is 1,000 0.6 millimeters. Okay. Oh yeah, I remember doing this one before. It's just like, well, like how do you kind of prove this? And so so now we're going to put this 58,000 pounds on something that's already 1,000.6 millimeters long. But let's say I don't know what the force I can put on, and but this thing already lengthened. You know what I mean? So I can only lengthen it up to 1,002 millimeters. But when I'm given it, it's already pre-stressed. You know what I mean? So even though like the stress, even though I pushed it this way and it squashed out the side and lengthened, that is, that's not a neutral. It's not like dropping something in the ocean and then doing your test down there. You know what I mean? Where I could take a 1 meter bar, or let's say I take a 1,005 meter cube of steel gets to the bottom of the ocean. All sides are now 1,000 millimeters. Don't quote me on this, but I think I can actually pull, axially. So I can have that cube, and I can just pull axially on it and lengthen it to 1,002 millimeters. So that could be that length right there. That is a neutral. But again, don't quote me on that. But I think that's the difference between something being pressurized on all surfaces compared to in material mechanics. You're just working with like, hey, we're squashing things, we're tensioning things, but we're not equally tensioning everything. It'd be impossible to do that. You'd have to have a vacuum to pull everything in all directions, or an ocean to like squish everything down in all directions evenly. But if you were able to do that, you would generate no stresses. But I have to research that, because it seems like, man, if you had like concrete columns, let's say even just concrete steel columns within compression, it's like if you threw bands that you could tighten, like hell yeah, then you could actually apply the same pressure, kind of on all surfaces. So you would have kind of pressure in all directions. So that might be synonymous with dropping in the ocean, and this idea that you're not going to get stresses that are pulling it apart. I kind of wanted to do this with chalk. It never really worked. And maybe I'm missing a fundamental. But I threw one of these pieces of chalk in a vise and then squished it. And then I thought that Poisson's ratio would change its length this way, but chalk not wanting to move in tension, being pulled outward, that it would split, in half, some way in half. It never really did that. But it did cleave at 45, or like steep angles. So maybe that's close to that, to what would be going on there. All right, hell yeah. So if we applied this 58,000 pounds, we would move it more. Like we would move it another 2 millimeters. You know what I mean? And so then the thing would be 1,002.6 millimeters, and we're over. We're 0.6 millimeters too much. So we can't actually apply this 58,000. So then the question is, if this is going to be equal to that, what's the max load that we can apply? All right, so I have a feeling this might not come out good at all, but we'll see. So we're going to put all right, hell yeah. Let's just come up with our own equations. So all right, so if we put a compression force, it's going to change in length. So we're going to put this load. I'm just going to call it P, and this load divided by 58,000 pounds per 2 millimeters. This would say that if I had 58,000 pounds, I would get 2 millimeters. So then we're going to add this to 1,000 millimeters. This is our original length, L naught, and this is going to be our change in length. And sure, this is stress, but I'm trying my hardest never not to use stress. I don't know. I think the term is confusing, but anyway, this is just change in length divided by the initial length. And so we can have a change in length of 2 millimeters if our initial length is 1,000. All right, hell yeah. I'm just going to continue on with what I'm doing. So we have 1,000 millimeters in length. If I put this load, divide it by 58,000 pounds times 2 millimeters, that's going to be the change in length. And cool. And then that... okay, yeah. And then this is going to be my change in length. So if I multiply that, this 58,000, if I multiply this by 0.3, that's going to be my change in length in this direction. And in this direction, I can only have a change in length of 2 millimeters. So if I have 2 millimeters minus this, that is going to be the remainder change in length that I can have up here. And that load is going to be that load also has to be P. That's going to be, we want this to be P and then this to be the load P. These two loads being the same. Alright, hell yeah. So that means that if I do have a load, P, and then we have 2 millimeters by 58,000 pounds, this is going to equal that change in length. Yep, because we're in tension, and so we have that load. It's less than 58,000, but when we but this number is going to be less than 2. It's 2 millimeters minus. Cool. All right, hell yeah. Might as well not do anything more. So here's our two equations. This minus this is change in length, and our change in length is going to be that. Yeah, let's just put those together. So we got 2 minus. This is going to be 2 divided by 58,000 times P is going to equal this, which is 2 divided by 58,000 P. And, bummer. Oh, no, we're right. So yeah, this is 0.3. Sorry about that. So this is 2 times 0.3. Okay, hell yeah. So now when we get this to the other side, we're going to have 2 is equal to, we can factor out the 58,000 and the 2. And over here, we're going to have 1 plus 0.3. Hell yeah. The 2's factor out, and whoa, we still have this load P. Okay, sweet. So then P is we're gonna bring the 58,000 to the top. 58,000 divided by 1 plus 0.3. Hell yeah. So now we get it. So we got 58,000 divided by 1 plus 0.3. And we get 44615. And this is our shear force. So the shear force is 44,615 pounds on a 1 inch, kind of a surface area of 1 inch squared. And then so what's the ratio? If we divide this by 58,000 pounds, when we would actually put something in compression or tension, then we get a ratio of 0.769. Cool. And, what's the square root of 2 inverted? Yeah, so it's 0.7. But, so this is why shear force is less. But a lot of literatures will use 0.6 or even 0.5. They'll say shear is half. So that's where maybe I have to throw in the towel on this model. But this model gets used for relating the angle right here to the normal forces that you can have. So if you're trying to relate the normal axial strains to shear, the angle of shear, shear deformation causing something to have angles, turn into like a diamond shape, then the relationship is, what is it? It's just 2 times the normal strain is that angle. So if we have for metal, it's 0.002, then the angle is going to be 0.004 radians. Alright, hell yeah. Alright, so I'm just going to leave it there. But yeah, it's just fascinating that this is a fundamental in material mechanics, is that when you do shear something, you're taking, and a 45-degree element will lengthen and compress, based on what we just did. And when it lengthens, or when you first compress it, hey, you can't lengthen it as far as you could, because that compression, due to Poisson's ratio, already lengthened it just a little bit. It only lengthened it a third. If Poisson's ratio is 1, then this load would be half. Like, it would be literally, that's probably a better way to look at this. Like, if I push in on this cube this way, and it shoots out the side, so if I put a load that moves it 2 millimeters this way, and then the thing lengthens at that 45 2 millimeters that way, well, we got to the 2 millimeters, and that's as far as we can go. So that's if Poisson's ratio is a 1-to-1. And then I can't put any force here. You know what I mean? So if I'm putting the equal amount of compression on that 45-degree element, then I'm only going 1 millimeter that way. If it squishes out 1 millimeter due to Poisson's ratio, then I can only lengthen it another millimeter. So then the load would be half, and then you know what I mean? And so, but yeah, just keep an eye on that, and then there sometimes just empirical values of someone saying, hey, this is the allowable shear based on what. But this is probably the best visual representation of what shear is, and how shear is causing normal strains. I mean, you're causing tension to failure. You're causing a tension failure as well as compressing that material, so your tension failure is going to be much less. So hell yeah. And then, because that happens just with axial loaded bars. If you first compress something, you don't get to tension it as much as you would have. And now the opposite is true. If you pull on something in tension, like it already compresses. And so so if you were able to pull on something this way, and then also pull it this way, you would be able to pull it the maximum amount. Yep, and that's one where I need to actually do that one myself. I should do that one this evening. I mean, if you pull on something this way and then also pull on it this way, I think you're going to be able just to do the max loads. The Poisson's ratios, I think, would cancel out in both of them. You don't get to add more to it, I don't think, but I think the Poisson's ratios would cancel out. But don't quote me on that. All right, hell yeah. So anyway, I'll try to get better at this shear, but I think it's there's elements of it that I think are more complex than the simple diagrams make it. Especially when that's a value of 0.76. That's pretty high when some books are just like, hey, shear force is going to be a half, 60%, 50 to 60%. Alright, so hell yeah. So I think I'll start in on this problem. How that relates to this problem is that, hey, this glue joint is going to be in shear, and so well, I guess from that aspect, the molecules are going to break, very similar to this. You know what I mean? Alright, hell yeah. So we're going to kind of wrap this one up, because I do want to do this problem. And, man, videos like these just make me, I don't know, like, is this worth it? You know what I mean? Is it worth it to turn on a camera and then struggle through something? Because I obviously could reach dead ends where, you know what I mean, like I just have to trash the footage. But I think we did pretty good. We got through this math, even though, like, I don't think I could even follow what I just did here. But anyway, just kind of just fighting for an equation. And I've done this before, but man, anyway. But yeah, so Yeah, so shear is going to have this effect. You're going to have compression and tension, and both are additive, where you're going to snap. Things will snap in tension when it comes to shear. If things are weak, yeah, things will snap in tension if something is weak in tension, like this chalk. This chalk is weak in tension. Now, if like metal can be ductile in tension, well, you know what I mean, that doesn't play by this rule of like saying, hey, when something gets to its yield point, its proportional limit, when you actually pull something and it deforms, it stretches permanently, things don't break there. You know what I mean? So if you are putting something in pure, torsion or pure shear, especially in torsion is pure shear, that's what we explained with this. If this was a ductile material, well, then this can lengthen more than 2 millimeters per 1,000 millimeters. You know what I mean? It can actually lengthen 5 to 20%. You know what I mean? So you could actually lengthen it by 50 millimeters. You could lengthen it, what's 5%? What's 1% of 10,000? That's 10. So yeah, 5%. Yeah, it's 50 millimeters. You could lengthen it 2 inches. You know what I mean? So this shape, this diagonal shape, could go 2 inches, and even skies, 5 to 20%. So you can just, if you have deformation and twisting even a steel bar, you could get that thing to just start wrapping around itself, and you're not going to get a clean helical break like we see here. And but I mean, once you start getting past the max force that you can do that, and then past that max stress, things will permanently, it won't go back to the same shape. So you still do have that aspect. But when it comes to failing, you won't see a break like that. What you see actually is just, you're able to just keep turning this, and then you get a break like this. You know what I mean? These will just keep turning, and then you'll just separate, and you'll have flat ends. Flatter than this helical shape. But still, this proportional limit, or this yield stress, still applies. It's just like, hey, if you put more force to cause, bigger than those loads that we talked about, then things will permanently deform, and that may be where people's lives are lost. You can lose your job. So, so you want to size less than that. And so, and those limits are based on this change in shape. So if this length gets too long, if this compression, oh yeah. So this is fascinating to me, because also steel can lengthen and compress the same amount. You know what I mean? Its strain, its normal strain and axial strain is 0.002, which is 0.2%. Or if I have 1,000 times 0.002, I just move the decimal. I've multiplied by 2. That's going to be 2,000, and then move the decimal place 1, 2, 3. So 1, 2, 3. That's how I get that 2 millimeters. So that's a good one to show. Now, like chalk might have 2 different values. You know what I mean? Maybe I can compress chalk like quite a bit. Even though visibly you can't really see it. But like concrete, maybe you can compress it quite a bit, and it might change length quite a bit. Don't quote me on that, but I do know that you can put more compression into concrete than you can in tension. And so, so now you can probably quote me on this. I mean, every material from a molecular level is linearly elastic when you put the loads on. And if we're talking about this region right here, it's all linearly elastic. And so you will get a change in length of a concrete pad being, in compression. But you take that same concrete pad and then put it into tension, like hell no, you can't change its length by very much. But yeah, those two don't have to be synonymous, though. You know what I mean? You might be able to change something's length quite a bit, but it doesn't take much force. So don't quote me that on concrete and rock being strong. It's very weak in tension. Doesn't mean that it has anything to do with the change in length being a big number or a small number. That's where the empirical aspect of material mechanics come in. You take a specimen of concrete, you pull on it, you measure the force that required, the force till it took to break it, and then you just measure measure that change in length. That's basically what you're doing. Load and change in length. Even though you're calling this strain, which is change in length compared to the length of specimen you were using, and now we have a parameter that's useful for every, length of concrete. You know what I mean? If I have a short one or a long one, measuring this specimen and taking this ratio allows me to figure out the change in lengths. But I think it's much more useful just to first and foremost know that a load will change its length, because that is very similar to a spring. You know what I mean? Force of a spring is the change in the length of the spring times some sort of constant. It's linearly related, and this is your constant that relates these two aspects. Same thing with load. You have load, and then you have a change in length, and then you have some sort of constant of integration that links the two. And that's where we take this load divided by area, change in length divided by total length, and that's where we get shear stress. The constant is the modulus of elasticity, and then this is strain. But I don't know, I think you just lose a lot even just going from here to here, even though that you have to work with these terms in the material mechanics books. But I think it's good to get out of those terms and see what they are from very practical purposes. Change in length is like, hell yeah, you could say something on the street, people would know that. Hey, I'm going to change this thing's length. I'm going to stretch it out. Compared to, I'm going to give you a number which is the ratio of change in length compared to the original length. That sounds like nonsense. All right, hell yeah. So this aspect is going on at that glued surface. You know what I mean? If we zoom into that glued surface, we got some sort of glue, and then and then we zoom in on a little square, and cool. We're putting a force this way. We're putting a force this way. We must have those counteracting forces, and then we can take a 45-degree element, and then we can see. All right, hell yeah. And we can see that that element is going to be in tension, and oh, yep. See, I can't see it from the free body diagram perspective, but from this shape, it's going to look like this, and so it's going to lengthen and compress. So there you go. So you get lengthening and compressing. It's going to look like that. All right. And hell yeah. And that's what's going to break it, I guess. Anyway, so that's where I got to end this. Holy Toledo. But we do have, even just for myself, I have to, keep saying that these relationships are empirical. You know what I mean? You put two glued joints together with a known surface area, with a known force, and put it in a device and pull on it, and guess what? You're going to get the max load, and then you know your area. So that's going to give you that PSI, that pressure. That's going to give you the force divided by the area, and that's going to give you the stress. And then here, we're not calling it sigma, we're calling it tau. This is going to be shear stress. I mean, it's fundamentally the same units as sigma, or, still in PSI, pascals, Newton meters squared. But this just indicates that you're pulling perpendicular to the surface area. So if the surface area is kind of pointed in that direction, your load is perpendicular to that face of that surface area, compared to if I'm, pushing two plates together, and the area here is in line. It's parallel with those loads being put on that. But then you just run experiments. You double the area, make twice the area, and then guess what? You get 2 times that force. And then so you kind of have this linear relationship up to a certain point. And if you do it, you can find this linear relationship up to the point where it's just like, no, actually, this thing moved over here, and now it's not even in the same location. But for this glued joint, you ain't going to be able to see that. And that's where, back to rubber, you can actually see the shape that's being made. And all right, so I think I'm done with this. I might tackle this problem. We'll see. But yeah, so this was going over shear stress. I don't know if I just try to make it more complicated. I don't think so. I think it's yeah, I don't know. I almost feel like it's an empirical value, because if you have like an element, pressure is what we would call, in or out. It's going to be yeah. So that's the thing that confuses me the most, is just like, is it a made up term? The fact that you have a shear, it's so that's where in the general definition of shear is the tendency to cause this deformation. You know what I mean? So it's empirical in the nature that we can set up this experiment of a rubber chunk and 2 forces, and we can see a shape that's being made, and then we can come here, and then that shape at some point might cause a failure. And why does it cause a failure? Because 2 things got too far away from each other. You know what I mean? And so that relates, and that's why that first part of the material mechanics book relates axial tension to shear stress. Normal strains and normal changes in lengths, because when we do shear something, we're putting 2 locations farther away, and we're lengthening that. You know what I mean? So on that plane, it's no different than that being an axial tension. And worse, it's being compressed in at the same amount, and we talked about how Poisson's ratio reduces then the amount that you can actually change this length, because it already squashed out a bit. So yeah, so there is some, from my perspective, there's some empiricism in the use of the term. Now, like, yeah, 2 wood boards being glued together, you still have a surface area and you have a force. Now, there is a relationship. That's kind of the empiricism. It says, like, hey, I apply a force, there is an area, and then I get a quantity, that pops out. If I'm given this area on this glued surface, I can put this much force. If I double that area, I can double that force. What stays the same is the ratio. The force per area is the same number. If this is the force per area, that's going to be the same number regardless. So if I triple the area, then I can triple the force if I 3 times the area. I think I'll have to research this, and I don't think I'm alone on this aspect. That when you have a 3-dimensional shape, and you say you have a shear stress that's acting perpendicular to the direction of this face, so that shear stress is acting perpendicular. Like, that's a bizarre term. Like in fluid mechanics, you're like, what are you talking about? Like a shear stress perpendicular. But maybe they actually do talk about that in fluid mechanics, and so I don't know. Like, I don't know where I get tripped up. The idea that we're labeling this, or the fact that it's different than normal and compressive stresses, which are similar to dropping something in the ocean or taking something and putting it in the vacuum of outer space. Like, shear stress is fundamentally different, but it still has the same units. Like, obviously you're applying a force on an area. You increase this, you can increase, you get to increase the force. So if you increase the area, you can increase the force. This number stays the same. Like, if this is your max number that you can have, so if you have sigma is equal to force divided by area, so if this number is what it is, and I increase this number, so and let's say I just have a value for this and this that make that number. Okay, and let's say I increase this one, I have to decrease that. So if I increase, oh damn it, no. The ratio has to be the same here. So if I increase the force, if I increase this double, then I have to double that. Yeah, because then that ratio maintains the same ratio. Oh, and I use the addition sign and I confuse myself. It has to be, you know what I mean, like plus 1 times 1. You know what I mean? It has to be multiples of. I can't just say the force, I can't just say it's plus 5 and then plus 5 on the bottom. Because if I have a ratio of 1/2, that's not equal to 1 plus 1, 2 plus 1. 2/3 is not equal to 1/2. But multiples of it, if I go 1/2 and then double this, I go 1 times 2 and then 2 times 2, so I get 2/4. That stays the same. Oh yeah. So I think I confused myself by, yeah, this is the number for the area. I'm going to, let's say yeah, whoops. So anyway, I think you see it. So you gotta, if you double the force, you double the area. That ratio is still the same, force over area. Okay, sweet. So yeah. So I want to learn as much as I can about shear, just because it's I swear, like the craziest symbol in material mechanics, and I don't know if it was all empirical, cool, but then stuff like this is just like, well, it's not all empirical, but then can we explain it at a molecular level as well? Anyway, so I'm just really fascinated with shear. Hopefully this was, I don't know. I don't think I'd watch this video, but I don't mind making them. So, hell yeah. Thanks for joining me, and that's a video.